Signals are everywhere. In the previous part, we explored the idea that space may be part of the larger system. But space is not empty. It is filled with overlapping signals moving in every direction at once. Every star, planet, and galaxy contributes to this environment through the signals we call gravity. So instead of thinking about gravity as a single isolated force between two objects, we can begin to think about galaxies as dense signal environments. And once many signals begin overlapping, a new question appears. What information might we be losing when we simplify all those signals into a single net result? Netting hides information. To explore this idea, let's imagine that gravity signals can be sampled and represented by small sets of vectors. For simplicity, we'll only use sets of 4 vectors at a time as our baseline simplified model. But in a real system, there could be thousands, millions, or far more overlapping signals. This way, we can preserve a target amount of the underlying structure, instead of simply combining those vectors into a single net result. And when we preserve more of the underlying structure, the intent is that we can begin extracting hidden patterns and correlations. Signal density matters. Let's start with signal density. Imagine 2 local regions of space that both produce the same final net vector after all the signals are combined together. In the first region, fewer signals are interacting. But in the second region, there are more overlapping signals competing with each other before collapsing into the same final result. From the outside, both regions appear identical once we reduce them to a single net vector. But underneath, one system may contain far more signal activity, interactions, and internal structure than the other. Cancellation patterns matter. Now let's look at cancellation patterns. In many systems, signals moving in opposite directions are combined together and treated as if they cancel each other out. But a region with large amounts of opposing signal activity may not be the same as a region with very little activity at all. Both systems might produce the same final net vector, even though one contains much more hidden interaction underneath. We may be losing information that could reveal hidden patterns and correlations, helping us refine our models. Hidden magnitudes. Cancellation destroys another facet of information in our models. Large opposing signals can combine in ways that reduce or hide their underlying magnitude inside the final net result. A system containing very large competing vectors may produce the exact same final vector as a system built from much smaller signals. Once those signals are compressed into a single net result, the larger underlying magnitudes disappear from the model. From the outside, both systems appear identical, even though one may contain far more energetic signal interactions underneath. So, the final vector may not fully represent the true scale or complexity of the underlying signal environment. An information systems approach. Galaxies are large, dynamic systems filled with overlapping signals, interactions, and repeating patterns. But when we compress those systems into simplified averages or net results, much of the underlying structure may disappear from our models. Instead of immediately reducing complexity away, we can begin by preserving more of the signal structure, adding back layers of information in manageable steps, and looking for hidden patterns, correlations, and constraints that may help us refine our models. This is the approach we can explore together in Darwin's Machines, 2024, where complex systems are viewed as information systems that store, process, and transmit information. In the next episode, we will explore how matter might respond to different signals and environmental conditions.